All right, so the title of our notes today is graphing the sine and the cosine function. All right, so the first thing you want to do is to recognize what one period or one pattern of that function looks like. Now both curves, if we took them off the x and y axis, would look very similar. You'd have this wave function that goes back and forth. Both the sine function and the cosine function look something like that. And if we find the middle of that function, say that's the middle of the function, the sine function starts at 0 at the middle and then reaches to its max, comes back down to the middle of that function, goes to the min, and then back up to the middle. And so that would be one period of our sine function. On the other hand, when you're looking at the cosine function again would start at 0, but it would start at its maximum, go down to the middle, then keep dropping to the min, back up to the middle, and then up to the max. So you want to know these shapes of the sine and the cosine function. Because when you're graphing sine or cosine, those are the shapes you're going to make. The only other possibility is if you have a negative sign in front of the sine or cosine, which would reflect these across the x-axis and flip them upside down, right? So those are our shapes that we work with when we graph these. There are two pieces, when I give you an equation, there are two pieces that you want to read off the equation. The first piece is the amplitude. And the amplitude is half the distance between the max and min values of your graph. So if we have a general equation y equals a times the sine of bx, or maybe we have a general form y equals a times the cosine of bx, that number in front of sine or the number in front of cosine gives us our amplitude. The amplitude would be the absolute value of a. So meaning it's got to be positive, right? So if there's a positive number in front of sine, you leave it positive, that's your amplitude. But if there's a negative number in front, you make it a positive number, and that's your amplitude. And that's going to tell us what the max and min would be, how high and how far down it's going to go. The other piece that we need to grab from the equation is the period of that function. The period of a function is the horizontal distance in or to complete one pattern. Okay. And the pattern I'm talking about is the pattern up here. You know, what I highlighted in yellow, that would be the pattern for sine. What I highlighted in green is the pattern for cosine. So what's that horizontal distance to complete one pattern? That's what we call the period of that function. And we can grab that from the equation as well. So if we have y equals a times the sine of bx, or if we're working with cosine and get y equals a times the cosine of b times x, and the period of that function is going to be 2 pi, right? That's a full circle. Remember, that's 360 degrees, divided by b. And b is that number in front of the x. So that's where we get that b from. So if there's no number in front of that x, that b is a 1, and so our period of that function will be 2 pi. But if we want to change the period of that function to something other than 2 pi, we can play with what number is going in front of x. Okay. Last thing, when we graph, we need to label the x-axis at every x-intercept, every max, and every min. Those are the places where you got to label the x-axis. Okay. So let's do this. First example. We're going to graph two periods of y equals 5/4 times the sine of, let's say, 1/2 x. Okay. So before you graph, you wanna find, well, what's my amplitude? What's the period of that function? So the amplitude, what is it? Yeah, it's the absolute value of 5/4, but 5/4 is already positive, so it's just 5/4. Right? It comes directly from the number in front of sine of 1/2 x. And then we go after the period of that function. Okay, and the period of the function is always 2 pi over b. Well, what's b in our problem here? 1/2. Okay, so 1/2 is b, so 2 pi divided by 1/2. Well, how do you divide by a fraction? We've had some practice with that when we're working, right? So this is 2 pi over 1 times 2 over 1, which is 4 pi. Okay. So then you have to have in mind what's the general shape of this sine function, right? How does it start? So I'm just going to put the x-axis down here first. Don't worry about the y-axis yet. Just draw a horizontal line. And the sine function starts at the x-axis, reaches its max, comes back down to the x-axis, goes to the min, goes back to the x. So I'm putting a point at each x-intercept, each max, each min, because those are the places where we're going to want to label the x-axis. And that's one period of the function. And then we're going to do this again, because we want 2 periods of the function. So easier to graph the pattern first and then put the x-axis together after, okay? So there's 2 periods of the function. First pattern is right here in yellow. The second period of that function just repeats that. I'm going to put the y-axis on here. Okay, y-axis goes through x equals 0. And then it's easy to put the amplitude on here. What's the max here, right here? How high does this thing go? 5/4. And how low does it go? -5/4. Okay. Now for coming up with the x-axis, that it can often pose the most problems, but it's actually not too bad. Because what the amplitude, what the period is telling us is, okay, the distance from here to here is 4 pi, and then the distance, the next one is going to be 4 pi, and so on. And we need to, I'm going to put tick marks on the x-axis for the parts that we need to come up with, right? So wherever there's an x-intercept, wherever there's a max, wherever there's a min, I need to come up with all those x values. Okay. The nice thing is these are equally spaced. Okay. And one period of that function, like if I put these equally spaced, is broken up into fourths. Right? So if we know the full period is 4 pi, and I want to know what 1/4 of that is, what do we get? Pi, right? And so for coming up with the x-axis, you always take the period and find 1/4 of the period in general.
And so because each period is broken into fourths, what we can do is take our period, find 1/4 of it, which is 1/4 times 4 pi, and we end up with 4 pi over 4, which reduces to pi. And so each tick mark we put on the x-axis, we count by pi. So we go from 0 to pi to 2 pi, 3 pi, 4 pi, that's one full period, and then 5 pi, 6 pi, 7 pi, and 8 pi for the completing the next period. And then we're done with our graph. Let's go on and take a look at example 2. Here we're going to graph 2 periods of the y equals 3 times the cosine of 5x. So we first asked ourselves, what's the amplitude? So we look at the 3 out in front, and we take the absolute value of that, which is still just going to be 3. And then we ask ourselves, what's the period of the function? In general, that's 2 pi over b, where b is the number in front of x. So this would be 2 pi over 5. And then note, we are graphing the cosine function here. Where in example 1, we graph the sine function. Here we're graphing the cosine function. So here's my x-axis. Here's my y-axis. And the cosine function starts at the y-axis at its maximum, drops down to the x-axis, goes to its minimum, back to the x-axis, back to its maximum. So that's one period of that cosine function. And I'm going to draw one more. It doesn't say which direction, so I'm going to go backwards this time. Alright, so we have one period on the left side and one period on the right side drawn. We know the amplitude is 3, so we're reaching a max height at 3 and a min at -3. We know the period is 2 pi over 5, and the period is broken up into 4 critical, evenly spaced critical points. And so what we do is we take the period and find 1/4 of the period by multiplying 1/4 times 2 pi over 5, and we end up with 2 pi over 20, which is pi over 10. And so we get to count by pi over 10. So 0 is on the x-axis at the y-intercept, and then 1 pi over 10, 2 pi over 10, 3 pi over 10, 4 pi over 10. And we can go backwards, 1 pi over 10, negative 2 pi over 10, negative 3 pi over 10, negative 4 pi over 10. And some of these can reduce, and so right now I'm just going to leave them as fractions with a denominator of 10 to see the pattern here. But yes, some of these fractions can reduce. I'm going to go over one last example, example 3 here. Asks us to graph two periods of y equals negative 5.72 times the sine of 3 pi over 2 times x. So again, we ask the question, what's the period of the function? Period's the absolute value of a. A is the number in front of sine, so this is the absolute value of negative 5.72, which makes it positive 5.72. And then, I'm sorry, that's not the period, that's the amplitude. Let me fix that. Then the period of the function is 2 pi divided by b, where b is the number in front of x here. So that is 2 pi divided by 3 pi over 2. So we can simplify this by writing 2 pi over 1 times the reciprocal of the denominator, so 2 over 3 pi, and getting 4 pi over 3 pi. Divide out pi from the numerator and denominator and get 4 over 3. That's our period of the function. And then lastly, notice our function starts with a negative. We've got a negative number in front of the sign, and when that happens, we're going to have to flip or reflect the sine function over the x-axis. So here's our x-axis. Here's my y-axis. And normally the sine function is shaped something like that, but we are reflecting that across the x-axis, so ours is going to look something like this. And that's one period of our sine function, and then we keep that going. One more period of that sine function. We need to label all critical points, which critical points are at maxes, minimums, and x-intercepts. And also on the y-axis, the max and min values, which come from our amplitude at 5.72 and negative 5.72. And to fill out the x-axis, we take the period and we find 1/4. In this case 4/3, which is 1/4 times 4/3, or 4/12, or 1/3. And so we are looking at a distance of 1/3. So first tick mark is 1/3, and then 2/3, 3/3, which is 1, and then 4/3, which is one pattern or one period of our function, and then 5/3, 6/3, which is 2, 7/3, and 8/3. And now we have all critical values labeled.